So here's the deal for today. What we're going to do is we are going to go over the introduction to robotics with the KUKA plugin. And at the end of class, if we have time, once we get through all of that, we will go over the last couple of problems from C# from last week that we did not get to in class. All right, so go ahead. The templates are posted on Canvas, both the Rhino file and the Grasshopper file. I will post the completed file on Canvas when we're done here. And if you don't have it, the only thing that's not going to work is this block right here. So you can follow along with everything else on how to get it set up with me as I go through. Does anyone not have the plugin installed? Okay. So what we're going to do, we're going to go through a couple of basic exercises with the robot. Just a brief note, when you're working with the KUKA plugin, all dimensions are in millimeters. So you're going to have to convert or just work in millimeters. So the template that Rachel provided has a base set that lets you draw lines with relation to the page. So you have a set of points on your toolpath, you have an angle of rotation for the robot arm, and a plane that the points are moved between. So you can see in Grasshopper that's going to show up robot arm and then the 2 points. And if you come over here, these are the KUKA components. They define the toolpath, the tool type that we have on the robot in the lab, as well as all of these settings. And this block is what's provided to you in the template. The slider steps through the simulation. So as you move the slider, the robot moves through the simulation, and you can see it goes to vertical and draws between the 2 lines and then returns back to the rest position. So what we're going to do is we're going to work through a couple of things. Really quickly, I want to take a moment and draw 2 points in Rhino. And I'm just going to bring those points into Grasshopper as a set of points for the robot to follow between. So draw your points, set multiple in Grasshopper, and we have these 2 points now loaded into Grasshopper. If we put these points into the XY plane component on the base, it's going to choose those 2 points to draw between. And you can see that the path trace turned orange. So if we try and trace that path with the robot arm, we're going to see that the robot turns red. That means that whatever the configuration of the orientation of the points are, the robot cannot handle that. He's all stretched out and confused. If you drag the points in, find my other point, they're way off in the distance. It will turn gray, which is an indication that the path is valid, even if it's in the table at the moment. So that's just to show you guys you can change the points. The robot will trace between the points in the same way that Grasshopper does. So it will go from point 0 to point 1 and so on and so forth. So let's say that we want to create a set of lines maybe for the robot to draw between. All right, so I'm going to take a set of points. I am going to use these 2 points that are in the file, in the template file already. And I'm just going to copy them a couple of times so I have a set. All right, I'm going to bring them in to Grasshopper. Drag this guy over and make Grasshopper a little bit bigger. I'm going to bring them into Grasshopper as a set of multiple points. And I need to see how they're being arranged. So I'm going to show with a point list what the points are doing. There we go. So we've got 0 in the back, 1, 2, 3, 4, 5, 6, 7. So we've got that funny 6. Everything else is oriented 0, 1, 2, 3, and then we have 5, 6 right next to each other. To get around that, what we can do is, instead of just moving the points, we can take our first 2 and move them in Grasshopper so that they're going to be oriented the same direction. But that then begs the question of how much we want to move our points, because we have to remember we are working in millimeters. So the conversion from inches to millimeters anyone know that number right off the top of their head? Probably not. 25.4 millimeters to inch, or inches to millimeters, I'm sorry. That is my bad, the wrong direction. So I'm going to say that this is going to be our inches slider, and we can rename it inches. And I'm going to give it a maximum of maybe 50. To convert our inches to millimeters, which is what the robot is looking for, I'm going to use a multiplication and a panel with the conversion factor for inches to millimeters, which is going to be 25.4. So we have inches going in, we have millimeters coming out, and we want to move based on this orientation in the x direction. We plug all of that in. We have 2 points, or 2 sets of points, which will be oriented correctly, 0, 1, and 0, 1 on the other set. Everyone with me so far? So the robot, we're going to look at that in a second, but the robot will trace between sublists, just like everything else we've done has. So if there are 2 zeros, it will read the first list, the first sublist, and then the second sublist, which is actually exactly what we're going for. We're going for a series of disjoint lines here instead of a polyline or a continuous. So what happens if we draw a set of lines between our points? The line between 2 points, this is going to work pretty much as we would expect it to. Our first set of points is going to be our A, our second set of points is going to be our B, and it'll draw 0 to 0 and 1 to 1. I'm sorry, we should only have one line here. There we go. Now that we have one line, we're going to move our line, and the robot will then trace multiple lines. So again, we're going to need our conversion factor from over here. We're going to create a series that's going to move our lines so that we have a series of, let's say, 3 or 4 lines. So I'm just going to say we're going to move it 5 inches instead of 25. And I'm going to set up a series, move series, just like we have all semester. So the step size is going to be our movement. I'm going to do 4. And we're going to move them in the Y direction. Need my move command. And they moved off of the table. So all I'm going to do is reverse my vector. And that's just going to multiply it by -1. So it's going to go the exact opposite direction. So over the table in template. I'm just going to slide everything down. I'm running out of room for it. So remember from what we saw right up here, that the robot is going to draw lines between toolpaths. So what we're going to do is we are going to find the endpoints of our line set. Anyone have any suggestions as to how would I want to do that? Okay. I'm going to do it the easy way, and I'm going to use an endpoints command and let that do my dirty work for me and find the endpoints of each line. We've got the endpoints. You can see them highlighted in Rhino. So now the question is how they're being arranged, because that's going to tell us how we want handle path. So we have one list, the start points, and we have the other list, which are endpoints. We need them to be on the same list, and we need them to go from 0 on the one to 0 on the other, 1 to the on one, 1 on the other. So this is going to be a weave issue. I'm going to use a weave command. I'm going to take my start list to be the 0 set and my end list to be the 1 set. My pattern is going to be 1 from the first and 1 from the second. 1 from the first and 1 from the second, which is the default on the component. Remember, if it wasn't, you would go in, set multiple integers, change your pattern. Well, cannot see. I have no idea why. Change your pattern and then hit commit changes. So now that we have our weave, we're going to bring this last component up and we are going to plug it into our XZ plane. And the robot, I know I have a white or a gray background on, the robot has now traced the toolpath that we want. It's gone from 0 on 1, 0, 1, 1, 2, 2, 3, 3. So if we trace the robot through that path, it will follow along the set of lines that we've defined and return back to the resting position. So what if we didn't want to have those diagonal lines, right? What if we want to have the robot arm retract between each of the lines so that it didn't trace that diagonal on whatever surface we're working on? We can do that in a couple of ways. But knowing that the robot arm traces between a set of points, what are we going to want to do? How are we going to want to lift the robot arm away from the table between each point? What we're going to do is we are going to change the elevation or add another set of points with a different elevation so that the robot arm has something else to trace to that's off of the table or off of the material that we're working on. So I'm going to bring my handy dandy unit conversion group down, which I have copied to my clipboard, and I will never copy anything else ever again because it's so useful. And we're going to move one of our sets of points. Which set of points do we want to move? The start points or the end points of this line? Come again? The end points, yeah. So which one is it tracing to first? Yep. And we want it to lift up at the end of each line, so we're going to move the endpoints upwards. And upwards is the Z direction for our orientation. So I'm just going to do the same thing. I'm going to just set up a move. It doesn't have to be a series. We're only moving things once. And I'm going to bring this guy over here. I'm going to grab the endpoints from the endpoint component. That's the geometry that we're going to move. And that's a long way up, and it doesn't need to be anywhere near that far. I'm just going to set it equal to 5. And that looks a little bit more reasonable. So now we need to get that into our other list. All right, so it's going to be another weave issue. But our pattern this time isn't going to be one-to-one, right? We have two different lists. One has twice as many elements as the other. So I'm going to use our old list for the 0 and our new list for the 1. But when we weave those together, if we look at how we're displaying our points, hide that one. Look at how our points are listed. We have 0 and then 1 is the above. So what we're going to do is we're going to change the weave pattern. Anyone have any suggestions as to what we want the pattern to be? Almost. So we have 1, this is our first, the bottom set is our 0 list, right? And the top set is our 1 list. So we need 2 from the 0 and 1 from the 1. So our pattern is going to be 0, 0, 1. And I'm going to set multiple integers. I'm going to stick another 0 in here. I'm going to commit changes. Now we have 0, 1, 2, 3, 4, 5, so on and so forth. It's hard to see against the gray background. but you can see that now we're tracing above the other points instead of in plane. So if we take this weave all the way back up into the XZ, we're going to get a robot path for it. And if we trace the path with the robot, it's going to come down to the start point, go up and across, down, and then come up and across. So we're going to get a set of lines instead of a set of diagonals. I'm sorry? It depends on the material you're working in. If you're, using a router and you're carving into fiberboard or foam or plywood, it's going to be different than if you're placing bricks on a wall, right? And that's what the assignment this week is going to be. If you haven't seen it on Canvas, you're going to be working on making a parametrically stacked brick wall and then using the robot to pick up bricks from a stack that you make and place them in the wall. So you're going to have to figure out, first of all, how to map points on the wall to points in the brick pile, and how to convince the robot that it needs to do it in a certain order. They're all going to be tools that we've used before. This is just a new application of lists. We're not doing anything new, we're just applying it to the robot. You just need to be really careful about how your lists are ordered, how you're weaving lists together, because what's probably going to happen is you're going to have a list for your wall and a list for your pile of bricks, and you're going to have to weave the two together 1-to-1 or 2-to-1. That'll make more sense when you look at the assignment if you haven't yet. So we've done that now. And let's look at changing the angle between the lines. So if you've been paying attention when we run the robot through the set of simulations, the robot arm is at 90 degrees. There you go, it's at 90 degrees to the line that it's drawing. We can change the rotation on the robot arm. So if you have some sort of directional tool, or if you want to carve in at an angle, it will do that when it actually carves in. As of right now, it's just going straight into the material and coming straight out. So if we want to change the angle of rotation, you can see we've got our angle set up here in a rotation. And what we're going to do is we are going to define a new rotation for the robot arm. All right, so we're going to use what we've worked on already. We have our 4 lines. We have a robot path that's going to retract between each line. And now we're going to add one more step that's going to change the rotation. So we have a set of items, and I'm going to first make sure that we have the same number of lines as we have number of angles. So I'm going to check the list length of our move command from up at the beginning, where we defined our set of lines in the first place. It's going to tell me we have 4 values. So what we're going to do is we're going to subtract 1 off from that list so that we're on the same number of lines and angles that we're going to step through. The panel will do just fine for that. And then, just like everything else we've done this semester, I'm going to set up a range. We need a set of values based on a number that we know. So our number of values is 3 from our subtraction, right? Number of steps. And then we're going to set up a domain using a panel. And our angles are going to be reversed. So instead of it being 90, it's going to be negative 90. Instead of 45, it's going to be negative 45. So we're going to go from perpendicular to a 45-degree angle to the surface. We have a range. We have 90, 75, 60, and 45. We need to convert our degrees into radians. And now we need to build a series. We need angles for the start, end, and retract points on each line. I'm going to use a series. I'm going to take from the list length as our count. We have four values. I'm going to create a new list by inserting items into a list that already exists. So it's asking for a list to modify, a set of items to insert, and an insertion index for each item. So our base list is going to be our rotational angles. The list that we're going to modify is our rotational angles. And our list, our index set, is going to be our list length. All right, so our new list is going to come out with 8 sets instead of 4 because we've inserted another 4 in. And you'll note that we have 2 of the same of each value. So we have an angle at the start point and an angle at the end point of each of our lines. We need an angle at the insertion point, so where it's going to rotate, right? To keep the robot or the tooltip from rotating while it's in the material or on the line, we're going to rotate between the end point and the point that we moved up, so our retraction point. So we need to weave our 2 lists together, so we have a total of 12 objects in our list, 1 for each of the points that we're tracing between on the robot arm. So I'm going to use a weave, and I'm going to take the list that we've just modified as the 0, and this set of 4 rotational points as our 1. And it's going to be the exact same pattern as it was before because we have a list of 8 that we need to weave into a list of 1 with 2 items from the first for every 1 item of the second. If I can get my integers to stay up long enough for me to actually edit them, we'll add another 0 in there, save our changes, and go forth. So here's the trick. We need to rotate, but which plane do we want to rotate in? All right, I'm going to use rotate in a plane or about a plane. We have our set of angles. We have our geometry that we want to rotate, but what plane do we want to use to rotate in? We're going to actually use the XZ because we need to rotate about the vertical, right? Yeah, so if we rotated in the XY, it would just rotate the tooltip, the tip of the tool around, and it wouldn't show any difference. It wouldn't show like a beveled edge or anything. So if we rotate in XY, it will rotate and change the depth or the angle of whatever cut we're making or whatever we're doing. So I'm going to do XZ. We're going to use our weave, and each of our rotations needs to be about the point that it's rotating about. Be our G and our P, our geometry and our plane of rotation. And now, instead of plugging rotation like we've plugged everything else into, we're going to plug this into the plane on the linear move command on the robot arm. So let's see if we can't figure out a way to watch this work. So we've got the robot arm coming in, it comes down at a 90-degree, not at a 90. Going to trace through, it's going to rotate. Not rotating the way we want it to rotate, right? You can see it's rotating the other direction. So a little bit of troubleshooting there. It looks like we need to rotate in the XZY plane, I'm sorry, instead of the XZ plane. So let's try that. All right, that looks much better. So if we hide our points so that we can actually see the robot, we can come back up here and step through 90 degrees, rotated to 70, 60, and 45. And then it's going to return to the original. So the biggest thing about the robot arm is remembering that it's going to trace between a set of points, not follow a line. So you have to define the points in the order that you want it to move to. And you can have it move between points. You can have it return to rest between points. If the robot arm turns red, will not work. Simulation will still run. The Grasshopper script will still work, but if we actually put it on the robot in the lab, it would not be able to do what we were asking. So one of the requirements for the assignment is that you don't have any collisions and you don't have any failures of the robot. So the robot should never turn red when you're working on the assignment. Quickly, I'm going to pull up Canvas and we will go over briefly the assignment for this week. So what we're going to be doing is creating a brick wall with a parametric curve or rotation of bricks. Take your pick. You're going to do that, and then you're going to create a stack of bricks for the robot to pick up and move with. The stack of bricks needs to have the same number of bricks as the wall that you've constructed. And then we're going to create a tool path for the robot to follow that it might use if it were stacking those bricks. All right, and that's the collisions and limited range of movement. The robot arm simulation should not turn red moving tool path. It'll show. So it'll show. The issue with the bricks you might not worry about the bricks colliding as long as you're taking from the top of your brick stack first. But when you're building the wall, you're going to have to build from the bottom up, right? So you're going to have to figure out, you're going to have to reverse one of your lists. And then when you're actually working in the KUKA plugin, you have a bunch of options. Settings, up. One of them is a collision option. I can't honestly remember if there's a good way. Collision checking is turned off by default. So really we're just going to be looking to see if the robot is running into the table or if you're like building your brick wall from the top down. The things that obviously wouldn't work. You can turn this collision checking on and it'll show you when it starts to run into things. But modeling masses for collision is a little bit hairy sometimes. So I just worry more about getting your bricks from the top of the stack first and putting them on the bottom of the wall first. And your parametric wall doesn't have to be anything crazy. Just have a curve or something in it that you can change. That one's pretty much up to you guys. I would just quality of life, I wouldn't recommend using more than 50 or 100 bricks because modeling that in Rhino gets finicky after a while, and when you have that many components, if you start changing one slider in Grasshopper, it's going to lock up for 30 seconds before you do anything else. Any other questions? All right, so we're going to start for the last 30 minutes or so of class. I would like to get pull up the in class actually. And we'll use the last 30 minutes or so of class for you all to step through that and finish working through the last couple of problems. Yep, or upload your Grasshopper file if you're using Grasshopper, or otherwise a screenshot of your notes or a PDF of your notes, or if you're taking notes on paper, a picture from your phone and upload it. All right. So we left off, I believe, all right, so let's go ahead and, if you haven't done it, go ahead and work through it. Otherwise, hang tight and we'll go over it in a minute. You're going to take your component that you created in number 5 and tell us when we can't divide by 0.